A network, in the context of electronics, is a collection of interconnected components. Network analysis is the process of finding the voltages across, and the currents through, every component in the network. There are many different techniques for calculating these values. However, for the most part, the applied technique assumes that the components of the network are all linear. The methods described in this article are only applicable to linear network analysis, except where explicitly stated. Definitions. Equivalent circuits. A useful procedure in network analysis is to simplify the network by reducing the number of components. This can be done by replacing the actual components with other notional components that have the same effect. A particular technique might directly reduce the number of components, for instance by combining impedances in series. On the other hand, it might merely change the form into one in which the components can be reduced in a later operation. For instance, one might transform a voltage generator into a current generator using Norton's theorem in order to be able to later combine the internal resistance of the generator with a parallel impedance load. A resistive circuit is a circuit containing only resistors, ideal current sources, and ideal voltage sources. If the sources are constant sources, the result is a DC circuit. Analysis of a circuit consists of solving for the voltages and currents present in the circuit. The solution principles outlined here also apply to phasor analysis of AC circuits. Two circuits are said to be equivalent with respect to a pair of terminals if the voltage across the terminals and current through the terminals for one network have the same relationship as the voltage and current at the terminals of the other network. It implies for all values of then with respect to terminals AB and XY, circuit 1 and circuit 2 are equivalent. The above is a sufficient definition for a one-port network. For more than one port, then it must be defined that the currents and voltages between all pairs of corresponding ports must bear the same relationship. For instance, star and delta networks are effectively three-port networks and hence require three simultaneous equations to fully specify their equivalence. Impedances in series and in parallel. Any two-terminal network of impedances can eventually be reduced to a single impedance by successive applications of impedances in series or impedances in parallel. Impedances in series. Impedances in parallel. The above simplified for only two impedances in parallel. Delta-Y transformation. A network of impedances with more than two terminals cannot be reduced to a single impedance equivalent circuit. An n-terminal network can, at best, be reduced to n impedances. For a three-terminal network, the three impedances can be expressed as a three-node delta network or four-node star network. These two networks are equivalent and the transformations between them are given below. A general network with an arbitrary number of nodes cannot be reduced to the minimum number of impedances using only series and parallel combinations. In general, Y-delta and delta-Y transformations must also be used. For some networks, the extension of Y-delta to star polygon transformations may also be required. The equations below are expressed as resistances but apply equally to the general case with impedances. Delta to star transformation equations. Star to delta transformation equations. General form of network node elimination. The star to delta and series resistor transformations are special cases of the general resistor network node elimination algorithm. Any node connected by resistors to nodes 1, n can be replaced by resistors interconnecting the remaining nodes. The resistance between any two nodes n is given by. For a star to delta, this reduces to. For a dangling resistor can be represented as either an ideal voltage generator or an ideal current generator plus the impedance. These two forms are equivalent and the transformations are given below. If the two networks are equivalent with respect to terminals AB, then V and I must be identical for both networks. Thus, Norton's theorem states that any two-terminal network can be reduced to an ideal current generator and a parallel impedance. Thevenin's theorem states that any two-terminal network can be reduced to an ideal voltage generator plus a series impedance. Simple networks. Some very simple networks can be analyzed without the need to apply the more systematic approaches. Voltage division of series components. Consider n impedances that are connected in series. The voltage across any impedance is current division of parallel components. Consider n impedances that are connected in parallel. The current through any impedance is for special case. Current division of two parallel components. Nodal analysis. 1. Label all nodes in the circuit. Arbitrarily select any node as reference. 2. Define a voltage variable from every remaining node to the reference. These voltage variables must be defined as voltage rises with respect to the reference node. 3. Write a KCL equation for every node except the reference. 4. Solve the resulting system of equations. Mesh analysis. Mesh. A loop that does not contain an inner loop. 1. Count the number of window panes in the circuit. Assign a mesh current to each window pane. 2. Write a KVL equation for every mesh whose current is unknown. 3. Solve the resulting equations. Superposition. In this method, the effect of each generator in turn is calculated. All the generators other than the one being considered are removed and either short-circuited in the case of voltage generators or open-circuited in the case of current generators. The total current through or the total voltage across a particular branch is then calculated by summing all the individual currents or voltages. There is an underlying assumption to this method that the total current or voltage is a linear superposition of its parts. Therefore, the method cannot be used if nonlinear components are present. Note that mesh analysis and node analysis also implicitly use superposition, so these two are only applicable to linear circuits. Superposition cannot be used to find total power consumed by elements even in linear circuits. Power varies according to the square of total voltage or current, and the square of the sum is not generally equal to the sum of the squares. Choice of method. Choice of method is to some extent a matter of taste. If the network is particularly simple or only a specific current or voltage is required, then ad hoc application of some simple equivalent circuits may yield the answer without recourse to the more systematic methods. Nodal analysis. The number of voltage variables, and hence simultaneous equations to solve, equals the number of nodes minus 1. Every voltage source connected to the reference node reduces the number of unknowns and equations by 1. Mesh analysis. The number of current variables, and hence simultaneous equations to solve, equals the number of meshes. Every current source in a mesh reduces the number of unknowns by 1. Mesh analysis can only be used with networks which can be drawn as a planar network, that is, with no crossing components. Superposition is possibly the most conceptually simple method, but rapidly leads to a large number of equations and messy impedance combinations as the network becomes larger. Transfer function. A transfer function expresses the relationship between an input and an output of a network. For resistive networks, this will always be a simple real number or an expression which boils down to a real number. Resistive networks are represented by a system of simultaneous algebraic equations. However, in the general case of linear networks, the network is represented by a system of simultaneous linear differential equations. In network analysis, rather than use the differential equations directly, it is usual practice to carry out a Laplace transform on them first and then express the result in terms of the Laplace parameter S, which in general is complex. This is described as working in the S-domain. Working with the equations directly would be described as working in the time domain because the results would be expressed as time-varying quantities. The Laplace transform is the mathematical method of transforming between the S-domain and the T-domain. This approach is standard in control theory and is useful for determining stability of a system, for instance, in an amplifier with feedback. Two-terminal component transfer functions. For two-terminal components, the transfer function, or more generally for nonlinear elements, the constitutive equation, is the relationship between the current input to the device and the resulting voltage across it. The transfer function, Z, will thus have units of impedance, ohms. For the three passive components found in electrical networks, the transfer functions are, for a network to which only steady-state signals are applied, S is replaced with j omega, and the more familiar values from AC network theory result. Finally, for a network to which only steady DC is applied, S is replaced with 0 and DC network theory applies. Two-port network transfer functions, in general, in control theory are given the symbol H. Most commonly in electronics, transfer function is defined as the ratio of output voltage to input voltage and given the symbol A, or more commonly, A, so that the A standing for attenuation, or amplification, depending on context. In general, this will be a complex function of j omega, which can be derived from an analysis of the impedances in the network and their individual transfer functions. Sometimes the analyst is only interested in the magnitude of the gain and not the phase angle. In this case, the complex numbers can be eliminated from the transfer function and it might then be written as two-port parameters. The concept of a two-port network can be useful in network analysis as a black box approach to analysis. The behavior of the two-port network in a larger network can be entirely characterized without necessarily stating anything about the internal structure. However, to do this it is necessary to have more information than just the A described above. It can be shown that 4 such parameters are required to fully characterize the two-port network. These could be the forward transfer function, the input impedance, the reverse transfer function and the output impedance. There are many others. One of these expresses all 4 parameters as impedances. It is usual to express the 4 parameters as a matrix. The matrix may be abbreviated to a representative element, or just these concepts are capable of being extended to networks of more than 2 ports. However, this is rarely done in reality because, in many practical cases, ports are considered either purely input or purely output. If reverse direction transfer functions are ignored, a multiport network can always be decomposed into a number of two-port networks. Distributed components, where a network is composed of discrete components. Analysis using two-port networks is a matter of choice, not essential. The network can always alternatively be analyzed in terms of its individual component transfer functions. However, if a network contains distributed components, such as in the case of a transmission line, then it is not possible to analyze in terms of individual components since they do not exist. The most common approach to this is to model the line as a two-port network and characterize it using two-port parameters. Another example of this technique is modeling the carriers crossing the base region in a high-frequency transistor. The base region has to be modeled as distributed resistance and capacitance rather than lumped components. Image analysis, transmission lines and certain types of filter design use the image method to determine the transfer parameters. In this method, the behavior of an infinitely long cascade-connected chain of identical networks is considered. The input and output impedances and the forward and reverse transmission functions are then calculated for this infinitely long chain. Although the theoretical values so obtained can never be exactly realized in practice, in many cases they serve as a very good approximation for the behavior of a finite chain as long as it is not too short.